An introduction to hypothesis testing about means. In general, a hypothesis test about the value of a population mean, mu, must take on one of these three forms. In the first box, we have a null hypothesis with the population mean, mu, being greater than mu0. Mu0 will denote a specific value in all of these hypotheses forms. We will use the sample mean value in order to test these hypotheses. Recall that sample means are normally distributed. And for normally distributed variables, the probability of being equal to a specific value is 0. Therefore, we should not focus on whether there is an equality sign there present in the null hypothesis for this case. In our second case, we have a null hypothesis, which is the population mean is less than mu0, which represents a specific value. Again, we will not focus on whether there is an equality sign here present in this null hypothesis. For our last case, we have a null hypothesis, which is the population mean is equal to mu0, a specific value. We will allow our x-bar value to vary in an interval when testing this hypothesis. We won't be focused on our sample mean value being an exact value when testing this last hypothesis form. The equality part of the hypotheses must appear in the null hypothesis when testing this form. Let's practice reading different scenarios and formulating hypotheses. Ceta County's EMS has recently received numerous complaints regarding its response time to emergency calls. Their EMS system has a goal to respond to medical emergencies with a mean time of 12 minutes or less. A local citizens activist group wants to conduct a hypothesis test to determine whether there is significant or sufficient evidence to prove that they are not meeting their goal. For this case, let's focus on the fact that we are trying to prove a claim to be true. Recall from the Introduction to Hypothesis Testing section, if we want to prove that a claim is true, we must state that claim as our alternative hypothesis. Here we want to prove that they are not meeting their goal. I always suggest that we start by stating our claims in terms of words and then putting them in terms of their statistical measures. This will help you in the last step, state your conclusion in layman's terms. So here we put as our alternative that they are not meeting their goal. Once we state our alternative hypothesis, we always put our null hypothesis first, and the opposite of that alternative would be that they are meeting their goal. Now, we state this using the appropriate statistical measures. The null hypothesis is that they are meeting their goal. Recall that their goal is to respond to calls in a mean time of 12 minutes or less. We can state this as mu is less than or equal to 12. The alternative that they are not meeting their goal would be that the mean response time exceeds 12. Example 2. Suppose a car company introduced a new midsize SUV and claimed that the new vehicle gets at least 32 miles per gallon on the highway. A competitor wanted to research the new vehicle and see if they can find sufficient evidence to reject the company's claim. We want to set up the appropriate hypotheses for this scenario. For this case, we are trying to find evidence to reject a claim. First, since we are trying to find evidence to reject a claim, we should state this claim as our null hypothesis. So we want our null hypothesis to be the claim that the mean miles per gallon for the new vehicle is at least 32, which means the alternative is the mean miles per gallon for the new vehicle is less than 32. Now we should state these hypotheses using one of our standard hypotheses forms. Our null hypothesis should be stated as the population mean is greater than or equal to 32, and our alternative hypothesis should be stated as the population mean is less than 32. Example 3. Mini-Mart began a new advertising campaign to increase their store's profits. Prior to the new campaign, their average weekly profits were $2,200. Formulate hypotheses that could be used to prove that their new advertising campaign has increased profits. We'll focus on the fact that we're trying to prove that their campaign has increased profits. Since we are trying to prove a statement true, we should state that claim as our alternative hypothesis. So here we start by writing our alternative hypothesis as advertising campaigns has increased the average profits. We'll now state our null. So notice, regardless of which one we write first, our null should always be written on top and our alternative should be written below. So now we'll state our null hypothesis as advertising campaign has not increased average profits. Now that we stated this in words, we can look at our three hypotheses about means formats and determine which is appropriate for this scenario. Our null hypothesis should be written: the population mean is less than or equal to 2,200. And our alternative hypothesis should be written: the population mean is greater than 2,200. Example 4. Crispy Oats cereal manufacturing company monitors its bagging equipment to make sure that the machine is working properly. When the machine is working properly, it fills 16-ounce bags of cereal. Set up a hypothesis test to determine if there is a problem with the bagging equipment. What null and alternative hypothesis would you use? For this example, the machine is working properly if it fills bags with 16 ounces. If it overfills the bags or underfills the bags, we would consider the machine not working properly. Therefore, in this case, this is an equality hypothesis test. With an equality hypothesis test, we don't have a choice. Our null hypothesis has to be an equality. The population mean is equal to 16, which in words is saying that the machine is working properly, and the alternative is that the population mean does not equal 16. which is saying in words that the machine is not working properly. Now I want to take a moment and connect some material that we've learned in previous sections in order to help us understand how they come up with test statistics and rejection rules for testing hypotheses about means. First, let's look at this form for hypotheses about mean. For this case, we have the null hypothesis is the population mean is greater than or equal to some value. For this case, our null hypothesis is claiming that the mean value is at least equal to mu0 or mu0 or greater. We're going to collect a sample of n items and compute the sample mean for those n items. If this hypothesis is accurate, our sample mean value should be greater than mu0 as indicated in this null hypothesis. Since we know that sample mean values are normally distributed if n is large enough, then we know whenever we're working with normal distribution, it is necessary in order for us to compute a z-score. Accordingly, the test statistic that we use in order to test this hypothesis is the z-score test statistic for x bar. Our z-score formula says that we should always compute the z-score for the value that you want the z-score for. In this case, we want the z-score value for our sample mean value minus mu, which is the mean for your random variable. And we know that the mean for the random variable x bar is mu, as learned in the previous section, divided by the standard deviation of your random variable. And we know that the standard deviation of the sample mean value, also called the standard error of the mean, is equal to the standard deviation divided by the square root of n. So accordingly, when we're testing a hypothesis of this form, this is the test statistic that we will use. Now, since x bar is normally distributed, we can draw our normal curve with our z-score of 0 here at the mean value. Now, if this hypothesis is true, then when we collect a sample of n items and compute the sample mean, our sample mean value should be greater than or equal to mu0, which should produce a positive z-score test statistic. So provided our test statistic comes back positive, it would be consistent with the null hypothesis. Since we have to acknowledge that this is only sample data and not the entire population, we have to leave some leeway for error. We know that we should come back with a positive z-test statistic. However, the question becomes, how much leeway for error should we leave? Or how far negative should we let our test statistic get before we conclude that this test statistic is so far beyond what our null hypothesis suggests that we should indeed reject the null hypothesis? For example, if our null hypothesis was the population mean is greater than or equal to 100, even if I came back with a sample mean value of 99 or 98, maybe even 95, I should give some leeway for the fact that this is sample data and not population data. However, there is a threshold beyond which I should be able to conclude that my value is so far below what the null hypothesis suggests, that this claim must be false. In other words, if I came back with a sample mean value of only 50, even though their claim suggested that the population mean value is at least 100. For this scenario, we call negative Z alpha our critical value because it's the value beyond which we decide to reject their null hypothesis. And our rejection rule is you should reject H0 if your Z test statistic is less than negative Z alpha, our critical value. If we set alpha sufficiently small, such as an alpha value of 0.05, this means that 95% of all values should be greater than the test statistic value, which corresponds to a negative Z alpha Z-score. Therefore, we're 95% certain that our rejection is accurate. So we should always set our alpha value small, as suggested in the previous section, whenever we're testing our hypotheses. Let's look at the case for the null hypothesis with the population mean is less than or equal to mu0. For this case, we will also use the test statistic that Z equals X bar minus mu0 divided by the standard error of the mean. If this null hypothesis is true, then when we collect a sample of n items and compute the sample mean, our X bar value should be less than mu0, producing a negative Z test statistic value. When we draw our normal curve, again, we set the Z-score as 0 at the mean, and we note that we should come back with a negative Z-score test statistic. However, once again, we have to acknowledge that this is only sample data. It's not data from the entire population. Therefore, even though we should get a negative Z test statistic, we have to leave leeway and allow that test statistic to be a little positive. In this case, we set Z alpha as our critical value. That's the point beyond which we decide we have found overwhelming evidence in order to reject the claim that the mean value is less than or equal to mu0. For this case, our rejection rule is reject H0 if your Z test statistic exceeds Z alpha. For our last case, we have the population mean equals mu0 as our null hypothesis. We have the same test statistic. For this test statistic, if the mean value equals mu0, like the null hypothesis suggests, then when we collect our sample of n items and compute the sample mean, that sample mean value should be equal to mu0, therefore producing a Z test statistic of 0. In this case, we have to acknowledge once again that this is a sample data that we've collected and that we're analyzing, and we have to leave leeway for errors. In this case, we have to leave leeway on both sides of the mean. So we know that our test statistic value should come back equal to 0, but we have to allow that value to get a little positive or negative before deciding to reject the claim. If we let alpha equal the total area in our rejection region, since we know this is symmetric about the mean, we say that the area in these rejection regions are alpha divided by 2. And our rejection rule is reject H0 if Z exceeds Z alpha over 2, or if Z is less than negative Z alpha over 2. Here we have the set of hypotheses, test statistics, and rejection rules for all three of our forms for hypotheses, for testing out hypotheses about means. Notice for this third case, we collapse the rejection rule. Reject H0 if Z exceeds Z alpha over 2, or Z is less than negative Z alpha over 2 into this one rejection rule. This rejection rule is reject H0 if the absolute value of Z is greater than or equal to Z alpha over 2.